All right, so welcome back. This example here actually is going to combine really three of the things we've been doing all into one problem here. So we want to compute the series for the function 1 over 1 plus x. And we're going to do it first with geometric series. So recall with geometric series the big main result we had, and that was that the series as k goes from 0 to infinity of x to the k is 1 over 1 minus x, and it'll converge provided that the absolute value of x is less than 1. So that'll converge when the absolute value of x is less than 1. So that's our series. That's our series. And again, it will converge as long as the absolute value of x is less than 1. So we want to use that to transform it into this form. So to transform it into this form, I have to replace the x there with a minus x. And so 1 over 1 plus x could be thought of as 1 over 1 minus a minus x. And then as long as minus x, absolute value of that, is less than 1, in other words, as long as x is between minus 1 and 1, that'll also converge. And what would that be? That would be the series, the sum, as k goes from 0 to infinity, of minus x to the k. Well, we can pull the minus sign out and get the series k equals 0 to infinity of minus 1 to the k, x to the k. And so that would be the series for 1 over 1 plus x. And that'll again converge as long as minus x is, absolute value of that is less than 1, which would be when x is between minus 1 and 1. So what would this look like? First few terms, k equals 0, that would be 1. K equals 1, be minus 1 to the 1, so it would be minus x. K equals 2, that'll become a positive sign again, plus x squared. K equals 3, that'll be a minus x cubed, and so on and so on. And plus x to the 4th, minus x to the 5th, plus, and then so on. Okay, so that's one way that we can represent the series 1 over 1 plus x. And we're able to get that by invoking our geometric series. The fact that the series, sum as k goes from 0 to infinity of x to the k, converges to 1 over 1 minus x, as long as the absolute value of x is less than 1. Okay, so that was part A. We did that with our geometric series. And we were able to use that substitution idea of substituting the minus x in. And that was, again, all going back to that theorem that we had before where we said if we had a function that involved a power of x, we can substitute that in, and then it will converge. It will converge to f of h of x for all x where h of x is in the interval of convergence. Okay, so that's one way. Let's turn to our second option, which is to do Taylor series. So we're going to use Taylor series around a equals 0. Okay? So part B. So our function is f of x equals 1 over 1 plus x, which we could write as 1 plus x to the minus 1. Then we're going to put over here that when we evaluate these things at x equals 0, we're going to put down my values. So for f of x, f of 0 would just be 1 plus 0 to the minus 1, just be 1. Okay. And then we need to compute some derivatives here. So f prime of x, we would multiply by the exponent. We have minus 1 plus x, and it would now be to the negative second power. We then evaluate that at 0. And that would just give me a minus 1. And then we would go f double prime of x, we would multiply by the 2. So it'd be a minus times a minus, which would actually be positive 2. 1 plus x now to the minus third. And we would evaluate that, f prime, double prime of 0, and that would just be a positive 2. And we keep going. A couple more derivatives here. Triple prime, we would multiply by 3. That would be minus 6. 1 plus x to the minus fourth. If we evaluate it, triple prime at 0, that would just be a minus 6. And the fourth derivative, we would multiply by 4. We get 24. 1 plus x now to the minus fifth power. And we evaluate that at 0, we would just get 24. And the fifth derivative, and then we'll kind of look for a general pattern. We multiply by 5, make that minus 120. 1 plus x to the minus sixth. If you evaluate the fifth derivative at 0, we get negative 120. So in general, the nth derivative, if you can kind of see the pattern here, first of all, it's alternating. 0th derivative was positive. First derivative was negative, second derivative was positive. Third derivative was negative, fourth derivative was positive, fifth derivative was negative. So it's going to have an alternating sign, minus 1 to the n. Okay. We're then multiplying by the next exponent after it. So for the sixth derivative, we'd multiply by the 6, and we'd actually have a 6 factorial. So that's actually n factorial. And then that's 1 plus x to the minus n plus 1. It's always 1 more than what it was. Okay? And that's how the derivative is always going to work. And so when you evaluate it at 0, that's just going to become 1 to any power, which is 1. So the big thing for us, the nth derivative evaluated at 0, will be minus 1 to the n times n factorial. And then we go to our Taylor series. Right, the Taylor series says the approximation is the sum as k goes from 0 to infinity of the kth derivative, evaluated in our case at 0, over k factorial x to the k. So in our case, we'd have sum as k goes from 0 to infinity of minus 1 to the k times k factorial all over k factorial x to the k. So our Taylor series would simplify to be sum as k goes from 0 to infinity of minus 1 to the k x to the k. That would be our Taylor series for this thing. And just to recall, let's compare that one more time. That was our series when we got from the geometric. It was the same exact series, minus 1 to the k, x to the k. Okay? These were both centered around 0. That's why x to the k is the power. So, once again, there we are. Okay, and then we have one final one to look at, and that is to look at this with the binomial series. Okay, so we turn finally to the binomial series. Part C, we're going to compare that with our previous two results. Okay, so the binomial series says that the sum is this. All right? That 1 plus x to the 1, what are we doing? Minus 1 here would be this series. So let's do it that way with binomial series now. Okay. So part C, 1 over 1 plus x can be thought of as 1 plus x to the minus 1, which we know would be a series as k goes from 0 to infinity of minus 1, choose k, x to the k. So now we start computing minus 1 to the k. Minus 1, choose k. Minus 1, choose k. So we just have to compute those things. Of course, we know this will converge by the result of binomial series as long as the absolute value of x is less than 1, which, by the way, we didn't do it, but we know that's the case here because that was the exact same series that we got the other way anyway. So that's going to converge as long as x is between minus 1 and 1. And so, of course, being the same thing, that would as well. So this one here, once we work out these minus 1 to the k's, choose k, this thing will converge between minus 1 and 1. Again, we don't know anything about the endpoints unless we test those individually. Okay, so up first would be minus 1, choose 0. But again, anything choose 0 is 1. So minus 1, choose 1. We're going to have a 1 factorial on the bottom, which would just be a 1. And since there's only one thing in the bottom, we'd only multiply one thing in the top. And so we'd have a minus 1. So we keep going. Minus 1, choose 2. We're going to have two things on the bottom, 2 times 1. And in the top, we'd have minus 1 times minus 2, which would just simplify to be a positive 1. And then keep going. 1, choose 3. On the bottom, we're going to have three things. 3 times 2 times 1. On the top, we'll have three things. Minus 1 times minus 2 times minus 3 is back to a minus 1. And so maybe one more. Minus 1, choose 4. We're going to have four things on the bottom. 4 times 3 times 2 times 1. On the top, four things. Minus 1 times minus 2 times minus 3 times minus 4. In other words, back to a positive 1. So hopefully you start to see that there's a pattern here. This is just going to end up actually being, well, on the 0 term, it was 1. First term, minus 1. Next term, positive 1. Then minus 1, then positive 1. And the next time, you're going to have 5 negatives on top. And those things will cancel exactly with all the things on the bottom. We'll be back to a negative 1. So in other words, this minus 1 to the k, choose k, is actually equal to minus 1 to the k. So that our series then must be the sum as k equals 0 to infinity of minus 1 to the k, x to the k. Okay, that's what our binomial series result has to be. So then finally put this all together. What was the result the first time? It was sum of minus 1 to the k, x to the k. That was using our geometric series connection. Using Taylor series, we got that it was also minus 1 to the k, x to the k. And now using our result for binomial series, we also get that it's minus 1 to the k, x to the k. It turns out, so these are all the same, and the reason they're all the same is because for a given function about a given center, there is only one power series representation, right? There is only one power series way to represent that function. Okay? There's only one power series representation for that function about that center. So our function was 1 over 1 plus x, and we're looking about the center x equals 0. Right? There is only one power series that's going to work. So even though we found this 3 different ways, the power series has to be the same. And so that was really what we wanted to kind of see, is do 2 things in this problem. First is to just review the first 2 ways of using these series the geometric series to generate a new series, and also to review Taylor series, using Taylor series to generate a new series, and then just to see another example here of this binomial series in action. But to find out in the end, they all go to the same result. They all come to the same result. So that's kind of actually cool that they all do turn out to be the same thing. All right.